Hello and welcome. In this video, we're going to take a look at some calculus on vector functions. So the moment that we invent a vector function and we have a function like r of t, which you can maybe think about as being the position vector of a particle at time t, well, we'd probably want to start taking a look at how that position vector is changing with respect to time. So we invent the derivative. And luckily, this is a lot like single variable calculus. So let's take a look. We could say r prime of t would just be simply the limit as h approaches 0 of r of t plus h minus r of t all over h. But then we might want to think about, what does a limit mean for a vector valued function? Well, let's start with an example in three-dimensional space, so that the function r of t could be component-wise f of t, g of t, h of t, which we could either express in triangle brackets with commas, or we could express that in terms of our three unit vectors I, j, and k. Well, if we are taking the limit as, let's say, t approaches some number, r of t, then this is simply just taking the limit of each individual component. And so because of that, the derivative is fairly easy to calculate. Using properties of vectors with component-wise addition and scalar multiplication, this expression, r of t plus h minus r of t all over h, and taking the limit as h goes to 0, can simply be written as just the derivative of each component. And then this would extend to any dimension, Rn. All right, well, in two-dimensional space, we might be able to interpret what r prime of t means. So let's let C be the space curve defined by that vector-valued function r of t. And it would have a direction. So as t is increasing, let's say that this blue curve here is traveling sort of up and then to the left and upwards again. So it has a direction in the direction of increasing t. And let's let r of t be just some sort of arbitrary vector at some point t, and we'll get a point on the space curve at point p with the coordinates f of t, g of t. Now, just for the sake of making this easy to understand, let's let h be maybe a positive small step, but h could also be negative. If h is just this tiny little step forward, then r of t plus h is going to get us a second position on the space curve. And then subtracting the two, we end up with the vector r of t plus h minus r of t being this red vector between the 2 points. Now it's simply just a matter of seeing how that changes as h gets smaller. So that's scaling the length of that vector by 1 over h isn't going to change the direction. But as we also let h get smaller, the points get closer to each other, we should have a tangent vector. Just very similar to how we invented the tangent slope for a function y equals f of x. And so we say that r prime of t is the tangent vector to the space curve C at point P here, provided that the derivative exists, so it has to actually be a vector, and the limits have to exist, but also r of t cannot equal the zero vector. And that is because the zero vector doesn't have really a direction, so it doesn't really mean tangent to anything. In fact, it's also orthogonal to everything. So as long as this vector has some sort of magnitude other than 0, we would say that it points in the same direction as the curve is currently traveling, and it is tangent. Now, we may also wish to get the unit tangent vector, and that is simply found by taking our tangent vector and scaling it to a length of 1 by dividing by the norm of r prime of t. Now, from the tangent vector or the unit tangent vector, we can even also give a vector form or a parametrized equation form for the tangent line at a point on a space curve. Let's suppose that P lies on a space curve here in maybe three-dimensional space. We know that r prime of t and t of t, the tangent vector and unit tangent vector, both point in the direction at which the tangent line should be pointing. And let's let r not be the position vector for the point P. Well, to get the equation of the line, for the tangent line, every point on that line can simply be written out as r naught, the position of point P, plus the parameter t times r prime of t, or we may use the unit tangent vector instead. That would just get us a set of points that are parallel to that vector passing through the point P. Now, you should know that there is the opportunity here where we can have the derivative maybe not be defined, or maybe the derivative could be equal to 0. And that would be some sort of interesting behavior where maybe the rate of change is undefined, or if you think about like a particle, it might be coming to a stop and then changing direction. So we can't really define a tangent line there. So we would say that if a curve has a derivative that exists over an interval and does not equal to zero, then it's smooth. But we can also take a look at curves that are not smooth, like that particle coming to a stop and changing direction and going somewhere else. So that's kind of an extra little definition here, smooth versus not smooth. So as I've mentioned, a major application here is thinking about this vector value function as being a position vector of a particle at a certain time. Well, we can extend this. The first derivative will give us the velocity of the particle, and that would give us a direction and magnitude. But then if we take the derivative of that, we also get acceleration. So let's do an example. The position of a particle is given by r of t with the components 2 cosine pi t, 2 sine pi t, and 9 minus t squared for any value of t from 0 to 3. And let's make a point where t equals 2 and find the position, velocity, and acceleration of the particle. Plugging 2 into the position function gives us the position 2, 0, 5. That's the current position at a time, let's say, of t equals 2. Now we need to take the derivative component-wise and then plug 2 in to find the velocity. So we'll take the derivative first, and then we can evaluate it too. And taking a look at this, we can see that right now it has no velocity in the x direction. It has a velocity in the y direction of 2 pi and a velocity component in the z direction of -4. So it's basically traveling parallel to the y-axis as it is falling down the z-axis. And if we want to, we could also relabel this as v of 2 for velocity. All right, now, one more derivative to get the second derivative for acceleration. And when we take the second derivative, we notice that in the z direction, we actually have a constant acceleration of -2. This might be kind of similar to how we would think about close to the Earth's surface, we have something falling with constant acceleration, essentially. So we could think about this, it's falling with a constant acceleration, and we may know from the behavior of projectiles with constant acceleration that it have some sort of parabolic shape to it, perhaps. We'll see what that looks like when we look at a space curve here. Now we just need to plug in 2 to get the exact acceleration at t equals 2. And so the acceleration at t equals 2 is -2 pi squared 0, -2. Now we might be able to kind of interpret this a little bit. We see that we've got a 2 cosine pi t and a 2 sine pi t. So it is having this circular motion. And whenever we have circular motion, you might be aware, the acceleration is towards the center of the circle, and that's what's making it change direction, but without having to get an acceleration in a rotational motion like that. It's traveling maybe at constant speed all the way around this circle. But then we also have the z component, 9 minus t squared, and that is giving us something that is falling from an initial height of 9, traveling downwards, and it's accelerating downwards. And you can see the acceleration is a constant -2. So let's take a look and see if we can plot this all and take a look at it in 3 dimensions to kind of get the sense of what's going on. All right, so here I've got a worksheet, and once again, I need some plotting tools, and I've defined our position vector function, and I've let P be the point r of 2. Now I'll plot the space curve given by r of t, and let's just maybe go from t equals, I don't know, maybe 0 to 2 is probably fine, I suppose. And well, that should get us kind of around one circle at least anyway. I've also got an arrow, and I've taken this to be the velocity, but I have actually gotten just a unit vector in the direction of velocity. So we can mostly just see the direction, and we don't really necessarily want to look at the length of that vector. And then I've got a unit vector in the direction of acceleration, r double prime of 2. And we'll plot them all at the same time and hope for the best here. There we go. You can see we are, in fact, accelerating downwards, and it doesn't look like a parabola, but it's slow, and it's going to be accelerating downwards. And you can see this green arrow is a direction of acceleration, and it is pointing downwards because we're accelerating downwards, but it's mostly accelerating towards the center of a circle. And then that red vector is the vector that we are having for our velocity. So you can see we're traveling around, and this red vector continues that direction. And maybe I'll plot once more to get 2 rotations around the circle. Of course, now with scale here, it's harder to see that this green arrow is actually pointing downward at all. Now, well, I guess this this thing crashes to the bottom when we hit t equals 3. So at that point in time, yeah, we hit the xy plane when we get to t equals 3. You can see the path of that particle. It's traveling in circular motion, and it's accelerating downwards towards the xy plane. All right, well, let's take a look at a couple other properties of the derivative of a vector-valued function. Well, similar to our conventional derivatives of real-valued functions, we have the addition and constant multiple rules. But when we start taking a look at product rules, things get a little more interesting. First of all, if we just have a real valued function multiplying a vector, then we can distribute that across all the components and then take the derivative of each component, applying the product rule on each component. And that would give us this generalized formula, f prime of t, that's the derivative of just the real valued function, times ut, that's the vector valued function, plus f of t times u prime of t. Now, maybe not too hard to believe that might be true, but you can prove that using rules of scalar multiplication of ft and u of t. But once we start getting into the realm of vector functions, we don't just have scalar multiplication, we have dot products and cross products. Again, this isn't too hard to prove, but you can probably believe that it's already going to be kind of similar to our normal product rule. This is using dot products though, so in order to prove this, you'd actually have to use component-wise multiplication, then use your differentiation rules, and then see if you can rewrite that in this other form, u prime dot v plus u dot v prime. What about the cross product? Sure enough, works pretty well as expected, but you do have to be careful with cross product because the cross product or Cartesian product is not commutative. U cross v and v cross u may have the same magnitude, but they are in opposite directions. So when we are using the product rule, you do have to be very careful. The order matters of all of our products. And last but not least, we can take a look at a particular chain rule where the vector valued function could be a function of f of t. And luckily, nothing unexpected here either. Really, this is just applying the chain rule on every individual component. And so as a result, just thinking we have this sort of scalar multiple f prime of t. And I maybe be confusing here. Maybe I shouldn't write that dot because this is just a scalar multiple. Now, with these properties, we can prove an important theorem that can be used to produce some results in a later video. Now, one way that this theorem could be stated is that if the magnitude of r is constant, then r prime is orthogonal to r for all of t. Another way to think about that, well, if r of t is the position of, let's say, a particle at time t, and let's say that's constant, well, that would be saying that the distance from the origin to this particle is constant. And well, if your distance from the origin is constant on a two-dimensional plane, that would mean that you're traveling in circular motion. If you're thinking about three-dimensional space, you're traveling somewhere on a sphere. Well, then your velocity, r prime of t, is orthogonal to your position. So you have this kind of idea. If you're traveling in circular motion, at any point, your position vector in standard position from the origin is here, r. And you can see that, well, whichever direction this is traveling, let's say the space curve is maybe traveling clockwise. Okay, well, if that's the case, then your tangent vector, you can see tangent to the circle here, this would be your vector r prime. And those should be orthogonal. And this can be extended to a three-dimensional sphere. Now, it makes sense. Let's see if we can prove that using these properties that we just came up with, especially those interesting product rules. Well, first off, we're going to assume that the magnitude of r is constant. So let's let the constant maybe be c. So let's assume the norm of r is c for all t. Now remember, to calculate the norm, you take each component and square, sum up all of those squares, and then square root. Another way we can calculate that is just the dot product of r with r, and then square rooting it. So we do know that r of t dot r of t, this is equal to the norm of r of t squared. So that should be equal to c squared. So r dot r is c squared, knowing that we've assumed that r of t has a constant magnitude of c. We'll start with this equation. We can take the derivative of both sides and use our dot product formula and use our product rule for the dot product. the derivative of r dot r. We get r prime dot r plus r dot r prime, and we have commutativeness with dot product. So that's simply just 2 of these r prime dot r's. We divide by 2, and we see that the dot product between r prime and r is 0. And that's the definition of being orthogonal. Now we can actually also reverse this whole process as well, and we can see that at no point in this step here should we not be able to sort of reverse the process. And so if r prime is orthogonal to r, we can also say that the magnitude of r is constant. And this becomes like an if and only if statement. Now we can extend this to the second derivative as well, and that is going to help us get that circular motion. We can see that maybe if the velocity of an object is constant, then its acceleration is orthogonal to the velocity. So we can either have 0 acceleration, which is orthogonal to everything, or our acceleration could be perpendicular, in which case we're changing directions without changing the velocity's magnitude. And that's going to put us into that circular motion. So hopefully that kind of explains that phenomena. As I say, that theorem can have some implications later on that's going to help us to look at things like the curvature of a function. And we can also take a look at how we integrate a vector valued function, but I'll save that for another video. So thanks for watching, and I'll see you in the next video.